Now we will see the demo video that how an PM interaction diagram can be drawn for a shear wall with uh, vertical gravity load and a uniaxial moment. So we will go to the design section, program list. Okay. Now this program is a basic program where you give the section of the wall and the load, and it will give an approximate percentage of steel required. Okay, so this program just find the approximate value of steel required. Okay, so we will see this program. Okay, this program draws the PM interaction diagram for a particular wall. We will draw a PM interaction curve for this section, that is C section, you can say. Okay, let us take an illustrative example. Okay, say we have a wall like this where the outer dimension, this is 1200. Okay, WD is 1500, WB is 150. So FP1, that is in dimension, is 900, right? And FT is 200. Okay, so we will take this section and say there are five number of steel layers. This is 1, this is 2, this is 3, this is 4. Okay, this is 5. The first layer is at a distance 50 mm from the compression phase, and the total area of steel is 402 mm square. Okay, okay. Now the second layer is at 150 mm from the compression phase, and the total area of steel in this layer is 402 mm square. Now the third layer over here, say we have 225 mm dia bars. Here also we have 225 mm dia bars. So the total steel in this layer is 425 mm dia bars. Okay, so the area turns out to be 1964 mm square, which, and the distance of the steel layer is 1125 mm from the compression phase, right? This distance. Similarly, layer 4, okay, area of steel is 1964. The distance of that layer is 1275 from the compression phase. And this is the last layer, and which falls at a distance 1425, that is from here to here, right? And the area of steel is 1964. So we will draw an PM interaction curve diagram for this section. Okay, just choose the section, right? Okay, now write FD. FD is 1500. Press enter key to save the value in the text box. Press enter. WB we have taken as 150. Okay, press enter. FB1 is 900. Press enter. FT is 200, right? Press enter. Now effective cover we have taken as 50 mm, right? We are taking effective cover as 50 mm, right? So 50, press enter. Number of steel layers 5, press enter. Okay, the first layer is at 50 mm from the compression phase and the area of steel is 402 mm square. The second layer is at 150 mm from the compression phase. The area of steel is 402 mm square, right? Now the third layer is at 1125 mm from the compression phase and the area of steel is 1964. Okay, so fourth layer is at 1275 mm. Distance is 1275 mm from the compression phase. The area of steel is 1964. Okay, now the last layer, that is fifth layer, is at distance 1425 and the steel is 1964 mm square. Okay, in that layer Fy is 415, Fck is 20, so the design load is 3000 and the moment that is to be carried is say 300 kilonewton meter. Okay, this is just an assumption. Okay, now this is for type 1 to 3. Okay, this is 1, 2 and 3. So this command is for that. This is for 4 and 5. This is 4 and 5, right? So let us click and draw the PM interaction diagram, right? So this is how you can draw the PM interaction curve for the particular wall section. Okay, now code is also given uh, the formulas for finding or for doing the doing the cross check for the permissible shear, that is shear in plane. Okay, this is the horizontal shear in plane of the wall. Okay, so code has given these formulas where the shear which we obtained over here should be less than the permissible shear stresses. If it is greater than, then you have to provide shear reinforcements. Okay, but your nominal shear stress should not be greater than the um, tau c max. Okay, so different formulas are given in the code. Horizontal shear in plane of wall. Okay, this is how we find the nominal shear stress of the wall. That is Vu is the shear force divided by T. T is the thickness of the wall into 0.8 times the Lw. Lw is the length of the wall, right? And you have to check for the shear at a distance. This is the critical section at a height lesser of these two, 0.5 Lw, that is zero point 0.5 into the length of the wall, or 0.5 Hw, that is 0.5 into the height of the wall. This is the height of the wall. Okay, so the permissible shear stress is also given in the code formula. Okay, these are the formulas for finding TCW depending upon the ratio. The height of the wall by the length of the wall is less than equal to 1 or greater than 1. Okay, so this is the minimum shear that is to be considered. Okay, and this is how you can find the horizontal and the vertical shear reinforcement required for the uh, horizontal shear in plane of the wall. Okay, so you just simply have to give Fy, Fck, height of the wall, length of the wall, T is the thickness of the wall, and the diameter of the bar you are going to use for vertical or horizontal reinforcement. Okay, and Bu is the shear force which we have obtained from the design. Okay, this is how you can also do the check the uh, case for horizontal shear. Okay, thank you.